All right. Hello. I am Juhan from the Department of Computer Science and Engineering, and it's a great honor to present my research in today's workshop. Today I am going to introduce about my research on mobile cloud cooperative AI platform for mixed reality applications. Just a brief introduction about me. I'm currently a PhD student advised by Professor Young-Hee Lee. I graduated my master's and bachelor's in the Department of Electrical Engineering at SNU. And my main research is related to edge AI systems and video analytics. So mixed reality, as many of you might have heard, is a blend of physical and the digital worlds, which unlocks the links between human, computer, and environment interaction. So by seamlessly combining the two worlds, MR apps enable unprecedented life immersive user experiences. And there's a lot of commercial products and services out there, and this mixed reality concept is becoming more and more close to our lives. So the core requirement of these kind of emerging MR apps can be classified into 4 categories. So first, an MR app needs to analyze the physical world to determine where to blend the virtual objects. Then it should generate the virtual objects, especially in the form of 3D media. And it should seamlessly render the generated contents for immersiveness. And finally, analyze the user interaction in real time to provide real-time feedbacks. And actually, all these kind of requirements is related to concurrent and real-time execution of multiple deep neural networks, or DNNs, and rendering tasks on resource-constrained mobile devices. There's a lot of emerging MR applications out there, like AI remote person finding, mixed reality office, or MR games, and so on. And as you can see here, these kind of like emerging applications all require around like 2 to 4 types of DNNs, which are repetitively executed per each high-resolution video frames. And the latency requirement is very tight, so as to provide a immersive user experiences. So there has been a lot of attempts to release these kind of like on-device AI frameworks to run these kind of deep neural networks on mobile devices, but we analyzed that is quite limited for these kind of like emerging MR applications. Specifically, they are mostly designed for a single DNN execution, and they cannot process very high-resolution videos in real time, not to mention that they cannot coordinate concurrent DNN executions and rendering tasks altogether. Another option to run these kind of like AI workload is to offload the heavy computation to a remote server with powerful GPUs. However, we see that such approach is also very challenging, mainly because offloading these kind of like high-resolution video frames incur a very large latency, even for very favorable networks like Wi-Fi in the 5 gigahertz frequency band. And you can see that, for example, here, offloading a full HD video for face identification takes about like as high as 3 or 4 seconds. And you can wonder if why don't we apply some kind of like image or video codecs like JPEG or so on. But we also observed that the accuracy sharply drops in the process. The core reason is because these kind of conventional image and video codecs like JPEG are human perception oriented, and when applied for AI inference, they incur a significant accuracy drop. So for example, consider upscaling that image in the left using a deep neural network-based super resolution. Here we can see that when we offload the data in the raw form, the accuracy is quite high. But if we start to apply JPEG compression in the process of sending the data back and forth between the mobile and the cloud, the accuracy drops quite sharply. So my research vision is to develop a mobile cloud cooperative AI platform for MR. And this is a very big picture that I am dreaming of. The core features of our platform can be summarized as follows. It intelligently splits the workload over the mobile device and the cloud for cooperative execution. We perform MR specialized mobile deep learning techniques across various system layers. And to realize my vision, I've been working at the intersection of mobile computing, AI, and network. And I have published papers on various top conferences and journals. So today, out of those projects, I would like to introduce the following two projects related to mobile cloud cooperative execution for MR workload, which has been published on ACM Mobicom and IEEE transactions on mobile computing. So the first project I want to introduce is Eagle Eye, which is an AR-based person identification system in crowded urban spaces. So basically what we want to do is design a remote AR person identification system over resource-constrained mobile devices like AR glasses or smartphones. So to motivate our work, we did a simple user study to analyze how difficult humans are, what difficulties humans faces in identifying persons in crowded scenes. So as you can see here, finding that person which stands in the middle of the scene, people take around more than 10 seconds. So basically what we want to develop is a AR person identification system where the user would scan the scene with his mobile camera, and the mobile devices run the multi-DNN based face identification workload and pinpoints where the target is. So the key challenge of designing such system is to run these multi-deep neural network-based face identification pipeline in real time. So as you can see here, to identify faces from the crowded scene, we first need to detect the faces, and for each face, apply these kind of super resolution network to enhance the resolution and then recognize it. So as you can see here, it involves multiple times of executions repetitively over a high resolution video frame. So yeah, our system architecture looks like this. So basically it is composed of multiple techniques to execute these compute intensive workload over the mobile device in the cloud. Just briefly introducing our key technique, we designed a technique called content adaptive parallel execution, which adaptively applies different pipelines depending on the scene content over the mobile and the cloud. So very high level operation of what we're doing is we first remove the background regions with no faces before feeding them into the face detection network. And out of the faces detected, we adaptively select the recognition pipeline based on its estimated recognition difficulty. And finally, from the observation that recognizing these kind of individual faces are independent, we run them in parallel over the mobile and the cloud for optimized latency. Just a simple idea of how we schedule the collaboration between the mobile and the cloud. We analyzed how whether each task in this multi-DNN pipeline is either compute intensive or network intensive. So basically, what we need to consider is how much data, what is the input data size of this task, and how much gigaflops is required for the deep neural network inferences. And the key idea here is that for the data, for the task with high input size and very small computation is more favorable for on-device execution, whereas the opposite case will be favorable for cloud offloading. Basically, so that's what we are doing. And with those kind of cooperation, we observed that our system achieves higher accuracy and latency performances compared to both the full on-device execution as well as full cloud offloading solutions, and with only around 100 kilobytes per full HD video frame. Yeah, so that was the first project. And the second project I would like to introduce is called Supremo, which is a low latency cloud-assisted super resolution and mobile devices. Yeah, so this is another work involving cloud offloading for this real-time AI model execution and mobile devices. Yeah, so super resolution is basically upscaling the input image into a higher resolution. And we observed that this is a core task for many emerging MR applications. However, we see that this is a very difficult and heavy workload because the inference complexity is very high because it involves a very large size, high resolution images, and it is very difficult to execute it in mobile devices. And as we have seen before, compressing the data size using the existing codecs incur a very sharp accuracy drop. So again, we designed a system that efficiently splits the workload between the mobile and the cloud to run this super resolution in low latency. And our system is composed of 3 key techniques. I'll just briefly give you the key idea. So the first technique is called priority ordering. So the goal here is to identify which part of the image I would like to send to the cloud so as to minimize the data size and thus the network transmission latency. Our key observation here is that given that input image, the compute-intensive deep neural network-based super resolution and a very simple image interpolation technique like bicubic interpolation differs only on the edges in the images. So basically, just by offloading only the image blocks with a high edge intensity and reconstructing the rest by simple interpolation on the local device, we can obtain similar performances as we have offloaded the whole image to the cloud. So that was about which data to send to the cloud, and let's consider the data flow back, going back towards the mobile devices. That is the upscaled high-resolution images. So basically, the output of super resolution is a upscaled high-resolution image, which is a whose size is very large and very hard to compress because of sharp accuracy drop. Here again, we take the optimized approach where we would send back not the whole upscaled high-resolution image, but instead only the residual signal, or the difference between the deep learning model's output and the simple interpolation method, which has a lot smaller entropy, meaning that it can be compressed more. And actually, we have observed that these kind of residual signals are more robust to these kind of compression process like DCT plus quantization. So basically, what it does is, given the mobile device's low resolution image, it first sends it to the cloud device, and while the cloud device is running the deep neural network-based super resolution, the mobile device runs the interpolation in parallel, and the cloud device encodes and sends the residual signal back, which is used by the mobile device to merge it with the bicubic interpolated image to reconstruct the high-resolution image. Yeah, so, and the final technique is related to called the offload inference pipelining, which parallelizes the end-to-end pipeline to minimize latency. So basically, the end-to-end cloud offloading process is composed of 5 steps. So sending the data to the cloud, running the deep neural network inference, encoding the data to be returned back, transmitting the data back to the mobile device, and decoding it. And as you can see here, all these steps consume different parts of the resources in the system. For example, at the network stage, mobile device side, and the cloud side. So basically what we're doing here is that we divide the image into multiple chunks, and we overlap different components in the offloading pipeline to minimize the latency. Yeah, and with these kind of techniques, we observed that our system achieves around 5 times latency acceleration compared to full data offloading, with around 15 times data size reduction. Yeah, and this is a visual example that our system identifies only the regions that are necessary to be processed at the cloud side, and it yields almost the same visual quality as if we offloaded the whole image, which would take a lot of latency because of its very high large sizes. Yeah, so as a summary of today's talk, so emerging MR applications require a concurrent multi-DNN and rendering execution on resource-constrained mobile devices. And to execute these kind of workload, mobile cloud cooperation is very crucial. And I am working on many projects to realize my goal. Yeah, so I am continuing my work to realize my vision. Just to introduce some of them, I am extending my work not just for these kind of like video processing workloads, but also for multi-sensor data streams like audio and video and so on. And I am also working on this end-to-end pipeline adaptation and joint scheduling approaches involving both the network transmission and the AI inference at the server side and so on. I hope that someday in the future I can introduce these kind of the progress in these kind of works as well. Yeah, and that's it. I'd be very happy to take any questions, and I am open to any discussions or collaborations, so feel free to reach me through my webpage or email. Thank you.